Welcome to Quest to Physics students. In this class, we are going to learn about some rules to solve the circuit students. Generally, circuits are some circuits are simple and some circuits are very complex. Okay, by using the Ohm's law, you cannot solve any circuits when they are complicated. At the time, we will use the Kirchhoff law students. First of all, we have to understand what is the Kirchhoff law is. Okay, students, Kirchhoff proposed two laws about solving the circuits. The first law is known as the Kirchhoff's junction law, students. Okay, students, the first law is known as Kirchhoff's junction law, and second law is Kirchhoff's loop law or voltage law. It has so many names. Kirchhoff's loops law or Ohm's law, voltage law, and also we call it as Kirchhoff's mesh law. These are the two laws, students. Let us talk about the Kirchhoff's junction law. Okay, students. It's a simple thing, students. You can understand very easily. It states like this, students. At a junction, the sum of the incoming currents are equal to the sum of the outgoing currents. At a junction, the sum of the incoming currents are equal to the sum of the outgoing currents. Here you have to understand what is the junction is. Simple, students, junction is a meeting point. It is the meeting point of two or more than two, students, not two or more than two circuit elements, students. Okay, students, circuit elements. In a circuit, there is a point there more than two circuit elements are meeting. Maybe some are active circuit elements and some are passive. Okay, students, how can you recognize one is the passive and the active? These are very simple, students. An active circuit element produces the energy, where the passive dissipates the energy, students. Generally, a resistor is a passive circuit element, students. It releases the heat. Okay, students, what I said, junction is the meeting point. Let's say it is junction. Let's call it as junction. There's a meeting point. Here so many wires are meeting. Let's say it's one more, and we have one. It is one, and finally we got one more here. Okay, students. Here we have four wires meeting at this point. That's the junction. Let's say a current is entering into the junction. Say the current is I1, and one more current is leaving the junction. Say it is I2, and here it is I3, which is entering into the junction, and here I4 leaving, and say it is I5. It is entering. It's a junction. Okay, it's a junction where circuit elements are meeting. Okay, 1, 2, 3, 4, 5 is it. In this one, I1. I1 is the current which is entering. And see, I2 is the leaving. I3 is entering. I4 is leaving. And I5 is entering. Here I am listing the currents which are entering. Okay. Currents entering at junction. Okay. What are these, students? I1, comma, I3, and I5. In the same way, currents leaving the junction. Obviously, it is I2 and here I4. What is the Kirchhoff's first law statement, students? We call it as the KCL, Kirchhoff current law, or you can write it as the KJL or KJL. This law states that at a junction, at a the sum of incoming currents are equal to outgoing. Okay, students. Let's assume that the incoming currents are taken as positive and the currents which are leaving the negative. Okay, currents entering a junction or there, some of the currents I am taking. I1 plus I2. I2 no, it is I3 and I5. Current leaving the junction. Okay, I4 plus I2. According to the statement, at a junction, the sum of the incoming currents are equal to outgoing current. These are the incoming currents and these are the outgoing currents. Or you can write it as I1 minus I2 plus I3 minus I4 plus I5 is equal to 0. Or it can be written as sigma I is equal to 0 at a junction. And we can state this one as in another way. Not like the sum of the incoming currents are equal to outgoing currents. Okay, students, this can also be stated as the algebraic sum of the currents at the junction is equal to 0. Algebraic sum of the currents at a junction is equal to 0. It is known as the Kirchhoff first law or junction law, students. Okay, students, and we have to conclude with one word here, students. Okay, this law is nothing but law of conservation of charges. Okay, students, it is law of conservation of charges, students. Here again I am saying at a junction, the sum of the incoming currents are equal to sum of the outgoing currents. It is known as Kirchhoff. Let's do one problem, students. Let's go with one example which depends upon the KJL, students. KJL, Kirchhoff junction law. Here it is a part of the circuit, students. These are the circuit elements. If you watch it, you will find the junctions here. Let's say it is the junction A, where 3 circuit elements are beaten. And we have one more, it's the B. And we got a junction here, it's the C. Let's say a current of 20 ampere. Current is measured in amperes, you know that, students. Okay, 20 ampere of current is entering into the junction. And from here, 30 ampere of current. Okay, from here, 15 ampere of current is leaving. Okay, students. And here, 10 ampere of current is entering into the junction. And he's asking, what is the amount of current is leaving this? Okay, traveling through this. Solution is very simple. According to the law, At a junction, some of the incoming currents might be equal to outgoing currents. These two currents are reaching the junction. That means what the sum is 20 plus 30. It is 50 amp current is leaving. Okay, students, here leaving the junction. And again, this 50 ampere of current is entering into the junction and 15 is leaving. That means what? It is 35 amp. Okay, students. Here, 35 ampere of current is entered into the junction and also 10 ampere is entered. 35 plus 10. The answer is 45 ampere. Okay, students. Let's see the problem again. According to the junction law, at a junction, the sum of the incoming currents must be equal to outgoing. According to junction law, at a junction, the sum of the incoming currents are equal to outgoing current. Here, 20 ampere and 30 ampere are incoming currents. The sum of the two might be equal to the outgoing. That is 20 plus 30 is equal to 50. Again, we are taking junction B. Here, 50 current ampere of current is entering and 15 is leaving according to the problem. Then, okay, the current which is leaving from the junction is 35 ampere. If was this, it is the junction C, where 10 ampere of current is entering and here the 35 is entering. And these two currents might leave the junction. That is 35 plus 10 is equal to 45. It is a solution of this problem, students. Students, now we are going to talk about the Kirchhoff's voltage law, students. Okay, students. The other name of this law is Kirchhoff's mesh law or Kirchhoff's loop law. Okay, students. The law can be stated like this. What's the Kirchhoff's voltage law or mesh law? The algebraic sum of the potential drops, listen my words, students. Algebraic sum of the potential drops in a mesh or a loop is equal to 0. The algebraic sum of the potential drops in a mesh or loop is 0. And you have learned the potential is taken as V is equal to IR by Ohm's law. Okay, potential, the potential difference can be had as V is equal to IR. V is the potential, I is the current, and R is the resistance. In previous videos, we have learned that what is the resistance is. Okay, students, watch it. If you are not aware of this, and you know that current is rate of charge in a given time, students, and potential differences, the amount of work done to bring unit positive charge from infinity to a point into an electric field. This is the potential, students. Potential generally measured in volt, students. Volt is the unit of the potential, and current is measured in ampere, and resistance is measured in ohm. This relation is that has three scientists and students: Thomas Volta, ampere, and as well as the ohm. Let's solve a circuit to understand what is the Kirchhoff voltage law. Okay, the statement goes like this, students. The algebraic, the statement of KVL, Kirchhoff voltage law. The algebraic sum of potential drops in a loop is 0. Or you can write sigma V is equal to 0, or it can be written as sigma IR is equal to 0. Okay, students. To understand this, we have to know a convention, students. Let's say it is a resistor. You are aware of this, okay, students. And we have one more resistor. Was this? It is the very important convention. And we got a cell, students. It is, and we had one more cell. Okay, students. This resistor has a resistance of R. Let's say it is the point A and it is the point B. Same as here, it is the point A and we are taking it as the point B. And it's also, say it is the C, it's the D, and here also it is C, and it is D, students. This is the cell, these two are the cells, and these are the resistors. Imagine that it's a part of the circuit and current is flowing in this direction. It's a sign convention, students. Okay, listen it carefully. It's the current which is flowing. Let's say the magnitude of the current is I. Okay, students. Here you know that resistance has the ability to interrupt the flow of the current. That means what it tries to stop the flow of the current. Isn't it, students? Here then we can write the potential drop across here is equal to I into R. Okay, students. Here see, current flows from higher potential to lower potential. Everyone knows this. Like the water flows from higher level to lower level. In the same way, current is also flowing from higher potential to lower potential. Let's say point A is at higher potential and point B is lower potential. And we are crossing this hurdle. That means we are losing some energy. So the potential difference or potential is dropped. The potential is dropped. The drop potential I am taking it as negative. Remember this. When you are crossing a resistor in the direction of the current, the potential drop would be minus I. Okay, students. The same way, see this? Okay. Yeah, we finish with this one. It's the direction of the current. Okay, imagine that you are traveling against the direction of the current. Okay, students. You are traveling against the direction of the current. Okay, students. Yet already I told you, when you are crossing the resistor, okay, potential will be dropped. The dropped potential is minus IR. But here we are traveling opposite to the direction of the current. It is minus of minus plus. It is equal to okay, see this. If you go through a cell here, it is the positive terminal and it is the negative terminal. You are crossing from positive to negative. Means what? You are losing. So the EMF might be taken as minus E. So this students. Okay, students. Here see, you are traveling in this way and you are raising it is minus to plus. Means raising, increasing. So you have to take it as plus E. These four things are very important, students. Once again, I repeat. Here, see, if you take a resistor, it is the resistor, and current is flowing in this way. It is at higher potential and this lower potential. Current always flows from higher potential to lower potential, and you are traveling. Just imagine, you are only traveling along the direction of the current, and this resistor has a resistance of R. To cross it, you have to consume energy. So the potential will be dropped. In this case, when you are traveling along the direction of the current and crossing the resistor, you have to take the drop as IR. Okay, students. The same thing I explained there. This time, current is flowing in the same direction, but you are traveling in opposite direction. Minus, you are traveling minus of this. Then potential drop is, but IR minus IR of minus, that is plus IR. Okay, students, and see here. Here it is the positive terminal, and the negative is at higher potential, and the lower, you are losing. That's why it is taken as negative. Then here, you are moving in this way. You are gaining, that's why it is taken as positive. This sign convention is very important to understand the Kirchhoff's voltage law students. Students, let's solve the circuit, students, which is shown on the board. Here, if you watch this circuit, you can find three resistors are in the circuit and two are the sources of EMF. Let's say we are at a potential of V1. So V1, it's V2, and it has a resistance of R1, R2, and R3. Okay, instead of this V1 and V2, you can take it as the E1 and I2 resistors. If you watch it, you will find a junction here, and we have one more junction. Say it is a reference point I am taking. It is A, and it's the B, it is C, it is D, it is E, and F students. You say this cell is giving a current of I1, and here it is given the I2. Okay, students, we have to write the equations by using the Kirchhoff voltage law from the circuit, students. If you watch it carefully, you will find two loops in. Okay, students. Okay, here let's go with this. We have a loop C. We started from A and travel through A, B, C, D, E, F, and A. In the same way, we have one more loop here. It is AB, EFA, and the third one, BCD, EF, EB. Okay, students. First I am taking the loop one, and I am traveling. Here I am taking this one as a loop. Okay, in loop A, B, C, D, E, F, E. Okay, students. Here I am traveling in anti-clockwise direction. The current I1 is flowing here. These are the wires which don't have any resistance. That's why no potential drop will happen in this spot. Okay, but it happens in between these two. Here it would happen in between these 2 points. Okay, but here there is no drop of potential. Then this current I1 is reaching this point B, and also I2 is reaching, and together the current is flowing I1 plus I2. The same current is flowing here, and it has to cross the resistor. Okay, according to the statement, the algebraic sum of the potential drops might be equal to 0, must be equal to 0. That sigma IR is equal to 0. Here also I am using the same thing. The total current is I1 plus I2, and it is crossing the resistor. Okay, students, here, how much current is crossing? It is I1 plus I2. Here, I1 plus I2. It's crossing. Just I am taking the product of the two. Here I am writing it as, okay, here I am writing I1 plus I2 multiplied with R. Okay, students. Here it is crossing. Already I told you how you have to take the sign convention. It is crossing, and you are moving along the current direction and giving it as minus sign. That's it. The point here also, the current is I1 plus I2. No current is changing. On reaching this point, I2 enters into the resistor as I2, and the remaining current is I1. this I1. Resistance. Here also this current has to cross this resistor. Then the potential drop is I1 R1. Same I1 R1. Resistance. Let's see, we are crossing in the direction of the current. That's why potential is dropped. Minus. Let's see. It's the minus, it's the plus. Okay, students, we are raising. Means what? Plus V1 or E1. I'm taking it as E1 now. The books you will get. There's the EMF. Okay, then we get as E1 and E2 plus E1 is equal to 0. It's the first equation. Okay, students. It's a loop A, B, C, E, F, E. Okay, students. Or you can write it as I1 plus I2 into R3. Okay, students. Plus I1 R1 is equal to E1. Another form of the equation. In the same way, we are taking this one. I'm taking this one, this mesh. I'm doing the same thing. I'm moving in anti-clockwise direction here also. I'm moved in anti-clockwise direction. Okay, I'm taking the loop. Or in mesh. Okay, here what it is? B, C, D, E, B. Okay, students. I'm traversing from B, C, D, E to B again. That means the current is I1 plus I2 multiplied with R3. That is I1 plus I2 multiplied with R3 as the negative sign traveled across. Okay, students, we travel along the direction of here. And here also I2 multiplied with R2. I2 multiplied with R2 travel in the same direction of the current and cross this. This is the potential drop, which is equal to minus R2. Here see, the minus is the plus. We are raising. That's why it is taken as E2 is equal to 0. Or in other words, you can be written as I1 plus I2 into R3 plus I2 R2 is equal to E2. This is the second equation. Okay, these two equations are enough to solve any circuit students. Yeah, but we have one more mesh here. I'm taking one more mesh. In mesh, okay, students, A, B, E, F, A. So, students, we are traveling against the direction. See, we are dropping plus to minus. Okay, minus D2. Here, see, we are traveling against the direction of the current. That is minus of I2, R2. Okay, students, we are traveling minus of minus R2. Okay, students, then see, we are going in this way. We are crossing. Here we are traveling. Here. In the same direction we are traveling. Minus I1, R1. We are raising plus E1 to 0. Resistance. Or it can be written as minus E2 plus I2 R2 minus I1 R1 plus E1 is equal to 0 or E2 minus E1. Okay, minus E2 plus E1 is equal to, I'm taking this on the other side, minus I2 R2 plus I1. In other words, you can read this 1 minus e2 secant. Okay, I2 R2 minus I1 is the equation what we need to use. I hope you understood what is the Kirchhoff's second law and how we can write the equations for the loop. If you like the video, please subscribe my channel. The next part of this video will do the problems which are related to Kirchhoff's first law and second law.